This week's long answer question is focusing on organic structure determination, and this is actually accessible if you've only done the AS side of organic structure, so in particular looking just at the use of infrared and mass spec alongside other clues in the question. So there are three different organic compounds, X, Y, and Z. They're isomers. So what we want to do before we get really into the table, because this is a longer mark question and it's using all the information in the table, but we don't want to forget that there is also information elsewhere in the question that we need to know. So they're isomers, fine. We've got molecular formula, so we need to know that in the question. We've also got a thing here that says none of the compounds are stereoisomers. Now, if you are still in year 12, it is most likely that the stereoisomerism that you have covered is EZ isomerism. And you may also, if you're in year 13, have done about optical isomerism. And both of these, so stereo means two, literally, like stereo vision means you have two eyes. Stereo means there's just like two sides, so EZ or the two different optical isomers, the two mirror images of each other. So all that means is there's not going to be either of those. So there are going to be no chiral centers. There may be carbon-carbon double bonds, but they are not going to have any option for being related as E or Z, and we will look at that when we draw our possible structures. So we need to go back to that later in the question. Okay, before we actually look at the information for infrared spectrum chemical test, most people rush into that. What we actually want to do next is look at that molecular formula and see what information we can get, because most people think that you can't get a lot of information from a molecular formula, but actually you can. And the information you can get is about to do with its general formula and the number of double bonds or rings in a compound. What do I mean by that? Well, we've got this formula C5H10O. Most of us know like the general formula for alkanes, CnH2n plus 2, alkenes, CnH2n. But we tend to sort of stop there and don't think about it when it contains an oxygen atom, but the same rules apply. So if I think about the ratio of carbon to hydrogen in this compound, it is 5 to 10. So it is CnH2n. Now, if that was just a hydrocarbon, we would assume that it was an alkene. We can't always assume it's an alkene though, because any time that I take two hydrogens off, what I'm doing is either making a double bond or I'm joining two carbons together to make a ring. So whenever I make two extra bonds between atoms that weren't there, that's when I have to remove hydrogen. So rather than overcomplicating it, let's just think that basically every time when we have two hydrogens less, that means either the molecule contains a CC double bond, the molecule contains a CO, so as we get more into doing aldehydes, ketones, carboxylic acids, we need to consider that C double bond O, or a ring, i.e. there is some sort of cyclic area where there are two carbons joined together to make a ring of carbons. So every time we remove two hydrogens, we reduce that carbon to hydrogen ratio. What does that mean? For example, if the formula was C5H8O, then I could have various different options. I could have two lots of CC. I could have two lots of C double bond O. I could have a CC plus a C double bond O. I could have a CC plus one ring. I could have two rings. Do you see what I mean? I couldn't have two rings with 5 carbons. It'd be too many. So we already know that my molecule either contains C double bond C, C double bond O, or a ring. So then we look at the rest of the evidence, which is going to be given by the infrared. So let's look at the infrared and the chemical test information together, because both of those things tell us about bonds and functional groups. The information from the mass spec will not be helpful until I've got a vague idea of the possible structures that these molecules could be. So we start with infrared because that tells us bonds, and it only tells us bonds. We then infer functional groups using the chemical tests. So let's have a look at molecule X. Molecule X has a peak around 3,500 and is broad. That is a clue for OH. 1650 is close to CO, but you need to be careful. Look at your data sheet because that is actually a C double bond C. So what we know is that X contains C double bond C and an OH. Now the chemical test tells us a little bit more about that. So that tells us alkene and alcohol. There's no carboxylic acid because there's no C double bond O. The reacting with bromine water doesn't really tell us any more information except for the fact that we know that it contains an alkene. Does not react with acidified potassium dichromate tells us about the OH group. It tells us that that OH group is a tertiary alcohol because primary or secondary would react with acidified potassium dichromate. So that tells me that my OH has 3 R groups attached to that carbon. Or it tells me that my OH is on a double bond because we know there is one present, and that double bond also does not have a hydrogen attached. Now that is, you may not realise that also sort of classifies as an alcohol that would not react with dichromate. It's far more likely to be the option where you simply have a branched carbon than it is likely to be sort of an enol, which is what that compound on the right is, where the OH is joined directly to the alkene. Okay, let's think about why. Why only has that OH bond in the infrared, does not react with bromine. So rather than just going, okay, right, it's just an alcohol, we've still got to remember that thing about the molecular formula, meaning it has 2 less hydrogens. So if it's got no C double bond O and it's got no C double bond C, it must be cyclic, and that's the most likely thing that people would miss in this question. So Y is a cyclic alcohol, but we also know that it is primary or secondary because it does react with dichromate. Then let's have a look at Z. Z, the infrared and the chemical tests are telling us once again that we have a CC and an OH. It reacts with bromine water. We know that it has an alkene group, it's not cyclic, and it does react with acidified potassium dichromate, so it also has primary or secondary alcohol present. So now we're going to take each one in turn because we've got all we can about what's present. So we know that X contains a C double bond C, an OH, and we know that it's a tertiary alcohol. And sometimes people sort of freeze at this point and go, oh my goodness, there are 5 carbons, there are so many options. There actually are not so many options because the C double bond C is going to account for 2 carbons. And remember, we've only got C5H10O to deal with. So let's say that we have that. We know that that's got to be attached to another carbon. We also know that our carbon that has the OH group has to have 3 other carbons attached. Now there's 1 attached already. So if I actually already put in, knowing that there is a tertiary alcohol, can you see that I've already basically accounted for the whole formula? And I've accounted for all 5 of my carbons. You only need to worry about putting the carbons in the right order. If it's got a double bond, it will have the right number of hydrogens. So if I just count 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1 for the alcohol is 10 hydrogens. So they should look after themselves because I know that I've put a double bond in, so I know the formula will be like 5 to 10 in terms of the ratio. Okay, we did say, however, that tertiary alcohol could also be this option with an OH, and then I've got a certain number of carbons left. So there are various ways that I could put those carbons on my carbon-carbon double bond. So what could I do? Well, I have 3 carbons left, so I could make methyl groups. These ones I'm not doing displayed because I'll run out of space. That would fulfill my no EZ isomers because I've got 2 methyl groups on 1 carbon. I could alternatively have 2 hydrogens just like I have here, double bond, an OH, and then I could have the remaining 3 carbons on here. Now, this question only asks for suggesting formulae. I would always go with sort of the simplest option. The simplest option to me is to have the OH on that tertiary carbon, so that one on the left, because I definitely know that that's a tertiary alcohol. And I definitely know there's an alkene. I also know, because of the 2 hydrogens on that carbon on the left, that there's no EZ isomers here. And if I'm going to go a little bit more advanced, I also know there's no optical isomers because there is no carbon that has 4 different things attached to it. Let's have a look at the different MZ values that we could have, and then let's see if we can match them up to this molecule. So we have 15. 15 is always CH3. It's not very helpful. Most molecules will have a CH3 group, and in fact all of these options do. Now let's have a look at 27. So one little clue is to have a look. See, there's only 3 different atoms here. So carbon, hydrogen, oxygen. Carbon is the most common. We could see whether our group, we think it contains oxygen. So if I take 27 and take away 16, then I'm left with 11. Now that doesn't work because carbon weighs 12 and I can't have 11 hydrogens on an oxygen, so it can't contain oxygen. So therefore 27 must only contain carbon and hydrogen. And don't forget also MZ values means they have a plus on them. That means it's going to contain 2 carbons because that's 24, which is closest to 27. So it's going to be C2H3 with a plus. So it can only come from this isomer here. What we need for that sort of low ratio of only 3 hydrogens but 2 carbons is the double bond section. So what we're looking at is this part of the molecule where we know we have 2 double bonded carbons and 3 hydrogens attached. Molecules are very unlikely to fragment across double bonds, so we're very unlikely to sort of chop that double bond up. It's much more likely to break in other places. When we get a large number like 59, the best idea is to look at the mass of the whole molecule. The whole molecule weighs 86. If I do 86 take 59, then what I get is 27. And so basically that other section of my molecule is the one that weighs 59. So that's the only isomer that will break up in that way and give those fragments. And so that's my final bit of proof that that is the correct molecule. I'm not asked to do any naming of it. I am asked to draw a displayed formula, which is why I've shown very carefully the bond between the O and H and all the methyl groups as well. So that is X. Now let's have a look at compound Y, and let's remind ourselves what we already know about it. So we know it contains an OH group, and we also know that that OH is part of a primary or a secondary alcohol. We also know that the compound is cyclic because we know that it contains 2 less hydrogens than we'd expect from fully saturated, but there's no C double bond C and no C double bond O. So the simplest thing that we can do is draw just a ring and include all 5 carbons. That's the most likely thing that we're going to have. So the reason that's most likely is because any rings smaller than 5 carbons actually kind of struggle to stay together because of the sort of very close quarters and the very tight bond angles that are involved, which are not like the 109.5 degree bond angles the carbons would actually prefer to have in order to minimize repulsion. So if you're thinking about cyclic compounds, the most likely will be the biggest arrangement. That doesn't mean that it couldn't be something else. So does this work? It works in terms of it's cyclic and it's a secondary alcohol, so it can be oxidized. We can take off 2 hydrogens and make a C double bond O. You could, if you preferred, draw a ring of 4 carbons. So this is also an option, and we could have, for example, our alcohol there. I'm not going to draw all the hydrogens on. Or you could have a ring of 4 carbons with a methyl group somewhere and an OH. So there's quite a lot of options, which is why we would like to go and look at the mass spec data to see. And actually, what we've got from the mass spec data is quite limited. We've only got 2 peaks told. That doesn't mean they're the only peaks, but those are the ones that have been told. So 17, straight away, when I have an alcohol, I'm going to think that that would be OH with a plus charge. When we're going to do that trick again of take 69, we know the mass of the whole molecule is still 86. We don't need to calculate that again because they're isomers. So 86 take away 69 turns out equals 17. So that is just the rest of the molecule. So that's going to have a formula of C5H9. Be careful because it's not going to be C5H10 because we've taken off the OH with a plus. Now, that obviously could happen with any of these isomers because if I take off the OH fragment, I'm going to be left with a mass of 69. However, we do the Sherlock Holmes idea of taking the simplest, most likely explanation is the simplest one, so therefore I'm going to keep it as my cyclopentanol, i.e. having a ring of 5 carbons. You would not get marked down. The other ones still fit. So the other ones still fit in terms of being primary or secondary alcohols, having a ring. If you are doing the full A level, if you're in year 13, you should know about optical isomers, however. And one thing that you should realize, for example, this molecule does have optical isomers, although it's in a ring, the ring is not symmetrical, and therefore that carbon counts as having 4 different groups attached. So just be careful about that. That would not actually fulfill our criteria. Now let's finally look at Z. Remember what we know about it is it does contain a C double bond C, an alkane, and it contains an OH, which is either primary or secondary. And then let's remember to keep it as simple as possible. So we also know it contains no EZ isomers, and the easiest way to ensure that is to simply put the double bond at the end so that we've got 2 hydrogens attached. Keeping it simple, because remember that the simplest thing that we can do is usually right. And so I'm going to put my other 3 carbons out of the 5 just attached in a chain, and because I know primary will definitely react, I'm going to stick the OH at the end. Now there's no reason it couldn't be somewhere in the middle, which is why we're going to use mass spec to see if that fits, because remember we're only looking for one suitable formula. So if this fits, we don't need to draw anything else. So one little tip for mass spec, there's quite a lot of stuff going on with this molecule. The most likely bonds, we can break off hydrogens. Breaking off hydrogens doesn't really tell us anything. It just takes 1 off the mass. So it's not really going to tell us much about where things are relative to each other. So what I'm going to do instead is I'm going to keep all the hydrogens attached, and I'm going to just rewrite my molecule as to the size of the fragments that would happen. What do I mean by that? Well, I'm going to draw 12 plus 2 hydrogens. That adds up to 14. That is double bonded to another carbon with 1 hydrogen. So that would be 13. I am putting the double bond in because remember, double bonds aren't as likely to break, and therefore I'm sort of trying to remember to myself that they're likely to stay stuck together. My next one is a CH2, so that's 14. Another CH2, that's 14. Another CH2, that's 14. And then an OH, I'm going to group that together. Because again, if the 1 comes off, it doesn't tell me anything, but I do know that OH is sort of likely to come off on its own. So what have we got? Well, we've got a peak at 27. And yes, my peak at 27 does fit because my C2H3 with a positive charge would produce that peak. What about 31? So 31 cannot be made of a combination of carbons and hydrogens, it actually has to include the oxygen. And if we're good at maths, you may have spotted that 14 plus 17 equals 31. So that peak can be CH3O plus, or because we happen to know the structure, we could be a bit more obvious about it and call it CH2OH plus. With the 59, that's quite a large number, so remember we're going to say the whole molecule weighs 86, take away 59. Well, once again, that just gives us this 17 fragment, which means that we have just lost the OH. 59 is not therefore a very helpful peak because we know it's got an OH group. So could we arrange this a different way? Well, we've already established from the previous isomer that the C double bond C needs to be like that in order to get C2H3. So the only way we can get C2H3 is if we've got 2 H's on one of the double bond carbons. So we want to keep that peak. So the only thing we could really change is the structure of this section here. So we could move the OH on this section, put it in the middle, but if we do that, we don't get our CH2OH peak. So actually this is the only possible isomer that will give us those MZ values in the mass spec. But because this question is just saying deduce or suggest, therefore most of the time you're going to have more than enough information to go on. So we had lots of information about chemical tests and all the different things that were going on in the infrared spectrum as well. You've got to remember about cyclic compounds because that really can throw some people, and then try to choose the simplest thing that you can. So try and go for the most obvious structure first. Don't do weird collections of molecules that you've never seen before.